today's lecture is all about, I guess, an introduction to a new section. But the good thing is you've seen some of this stuff before. Now, in 1231, this is actually the first topic. Parts of this section 3 are in the first topic, but only the basics. Can I just have a show of hands? Who sort of has some vague recollection of functions of two variables from last year? Okay, because you would have done partial derivatives and a few applications and things like this. Now, how is this different to what you've already learned? It's a good question. Well, you would have seen a few of these ideas, but not at any depth. Okay? And in particular, we'd never talked about limits and continuity, differentiability, gradient, directional derivative, and Taylor series for functions of two variables. So what today's lecture, I guess, can be viewed as is just a little reminder on what you should already know. Now, tomorrow we'll start limits and continuity, and that's going to be a whole new ball game. So, that's... I guess in one sense you can think of this section as, last year, for example, you would have looked at functions like this, functions of two variables. In a vector context, what happens if I write the independent variables as a vector? So, compared to the previous section where we were looking at functions of one variable that had vector-valued outputs, this is different. Now you've got a vector-valued input, and the output is a scalar or a real value. So we're kind of mixing it up a bit. Anyway, we're going to look at these three things today. All right, so functions of two variables. Two or more. Now, one of the motivations for studying functions of many variables is that, again, you've got a degree of flexibility with them, okay? And in particular, complex phenomena usually depend on two or more things. Okay, so for example, this is an example that I put in first year. Wind power is becoming increasingly popular. And you can derive the following representation for the power in watts available to a wind turbine. And the power depends on the radius of, the diameter of the turbine blades and the V, the wind speed, and a few constants. So, we can sort of speak of this relationship up here as a two-variable dependency, okay? The function involves two things, R and V. Now, you can take that a step further and look at functions of three variables, functions of four variables, functions of n variables, okay? If you did that, then your input would be like a n-tuple vector. Now, back at school and in first year, you looked at functions of one variable. So the independent variable here, in this case, is just x. And you developed curve sketching skills and differentiation and integration and limits and things like this. And so what we're going to do in this section is extend these ideas to functions of two or more variables. Now, this course is about vector calculus, calculus of many variables. If we're going to extend that, then we should look at derivatives, integrals, and I guess concepts related to the derivative, like the chain rule and things of this nature. Now you may think, oh, okay, it's easy. We just, it should, I know calculus pretty well. It should just readily generalise. Well, sometimes this is the case and sometimes it's not. All right, so let's look at some basic examples. Now, just a bit of notation first. If you want to, you can write this as this, okay? If you want to. It sort of gives it a vector, you can relate it back to vectors. Now, technically, f's the function here. X and y are the two independent variables. So if you change x and y, you change the output, right? But, sometimes we break the rules and we actually write z equals f of x comma y. Technically, z's got nothing to do with the function f, right? So really the function is f there, not z. But we break the rules occasionally. Now, if we're going to have two inputs into our function, x and y, it would make sense for those to come from a two-dimensional set, right? So what we denoting over here is that this is like a domain. Now, for functions of one variable, the domain is just like an interval or a point or the whole real line. For functions of two variables, you take one line and cross it with another line, you get a plane. So it's a two-dimensional thing usually. Okay? So let's look at some examples. This is the notation. So f maps some subset of the plane, the set of real numbers squared, and you output a real number. So let's look at some examples. Suppose I'm defining three functions. I can put in any real number, x and y, into here, and out will spit a real number. Over here, I have to be a little bit tricky to make sure I'm not dividing by 0. So the domain for this second function is all those points in the plane such that the denominator's not 0. So what would that look like? Well, you've got the plane and you just pull out the points on the line y equals 2x. So imagine this is the domain. You pull out this line. So it's every point except for the points on this line. That's the domain of this function. Here's a third function. Root x plus y. Again, you have to, we're dealing with real numbers here. So you just want to make sure that the x plus y is non-negative. So what would that look like? So the domain would be in there. Okay, so even more simply, just think about your function as a machine. You've got two inputs. Your f goes to work and it outputs some value, f of x comma y. That's as simple as I can make it. Okay? So if you wanted to sort of even relate this back to vectors, you input some vector, you output some real number. Okay, so hopefully everyone's pretty comfortable with that. What we're going to do is just review visualising and sketching. Now you might think, hang on Chris, we already looked at this last year. And that's true, but not in any depth. And secondly, in the second half of this course, you are going to have to know surfaces like that. Okay? You give it an equation, is it a cone? Is it a cylinder? Is it an ellipsoid? What is it? Why? Because at some point, you're going to have to integrate over those surfaces. So the region of integration later on in the semester is not going to be an interval, it's going to be a surface. Okay, it's very hard to integrate over a surface if you can't describe it or recognise it. That's the motivation for learning surfaces. Okay? All right, so some basic definitions. So the set of points where our function of two variables has a constant value is called a level curve of f. We can speak of this triple being a set of points in space being the graph of f. And the graph of f is also sometimes called the surface z equals f of x comma y. So these are all acceptable. Usually from the context, it's clear what you're talking about. So if I talked about a function z equals x squared plus y squared, that would be okay. I'm technically breaking the rules, but that would be okay. All right? Then you think, oh, do you mean the surface or do you mean the function? Well, sometimes that's not so clear. Now, level curves, and also another idea called contour curves, in part play a big role in being able to sketch surfaces or helping us to determine what a surface looks like. So we'll have a look at that. But before we get to that, let's just try to visualize what the graph of a function might look like. So here's our three-dimensional space, and I've sort of drawn in you can imagine the axes sort of running along here and along here. Here's the origin. And you can think of that shaded rectangle as being a domain for this particular function. So think of this set as the domain of the function. In particular, note that the domain is, in general, a two-dimensional set. Okay, it could be a line or something, but in general, it's a two-dimensional set. Now, for each point in the domain, in the xy plane, right, I'm going to have a corresponding point on this surface. So all I basically do is, if I'm at a point in the xy plane, I just look up or down, and I'm going to, I sort of go up to the surface, or the point on the surface. Okay, I guess that should be a special r here, because we're talking about r cubed. Now in this particular picture, the surface lies above the xy plane. It's not always the case. It could lie below the xy plane, or it could intersect at some point, or along some curve. Okay, but this is just a real simple diagram. Okay, so suppose we're given a function, we want to determine what kind of surface is associated with that function. Essentially, what we learnt last year was to examine how the surface intersects with various planes. Anyone remember that? So you look at sort of horizontal planes, and you look at vertical planes, and you look at the intersection, and you get a whole bunch of lines, and you move those lines around, and you link them up somehow and get a surface. Well, let's review that. Let's talk about that a bit more. I've already defined what I mean by a level curve. A contour curve is essentially the same thing, but it's not necessarily drawn in the xy plane. Now, I've got a good picture in a minute to really show you the difference between the two. So geometrically, a contour curve is just the intersection with a horizontal plane and a surface. And that curve is drawn in the plane. In this case, z equals a constant. If we sketch all of those contour curves down in the xy plane, and again, I'll give you a good visualization of this in a minute, then we call those special curves level curves. So let me show you what I mean. It's best if it's just illustrated with a picture. All right, so here's a good picture. Now you may look at that and go, well, hang on, Chris, the surface is already there. Well, we'll get to drawing surfaces in a minute. Okay. All right. So here's the function. Oh, hang on. Here it is here. Okay. So this is just f of x, y. Now, in that picture, what's happened is that yellow horizontal plane, which is parallel to the xy plane, intersects the surface, and you'll see we've got a little circular kind of curve there. Okay, so essentially this is it. This lies in the plane z equals 75. You put 75 in here, and you rearrange, and you get this. Now, if I draw the same circle in the xy plane, then we call it, this particular circle, a level curve. It's the same circle, just drawn in different planes. Okay, so how does this help us? Well, that gives us some idea of the cross sections of our surface parallel to the xy plane. And as we're going to find out, that's quite handy. It's going to be quite handy. Okay, so here's some surfaces and the level curves associated with them. Now, what I'd like you to try to do is visualise how the level curves and the corresponding surface on the left, like the connection between them. So think of all these lines as representing sort of, I guess, you're slicing the surface, and these lines are going to be where the slices are. Now you'll see in some pictures, the lines are closer together. Say here they're close, and then here they're not so close. And here they're, well, there's not as much variation as up here. Can anybody tell me, or remember from last year, what does it mean when all the level curves are close together? Yeah. So one way to interpret having these level curves close together is that the surface is either, increasing quickly or decreasing quickly in some sense. Again, try to look for patterns between, I guess these peaks and these circles. Okay, these peaks here would refer to here, and the little ones around it. Okay, here's some more. Again, on the right-hand side, we've got the level curves. On the left-hand side, we've got the corresponding surfaces. So all you do to get those level curves is you set f of x comma y equals a constant, and then you set, c equals 0, 1, 2, 3, and look at the curves. And we'll do that in a minute. Okay, so let's put it all together. Sketch the surface. Anybody know what kind of surface it is? Anyone? So it's almost, well, I guess you see the x squared plus y squared, you think, oh, maybe it's a circle or something. Not quite. Not quite. Let's investigate. So I'm going to do this two ways. I'm going to use level curves and contour curves, so just using horizontal planes. And I'm also going to use vertical planes. And I'll show you how that gets done as we go along. So we form contour curves. from the equation c equals x squared plus y squared on 9. Now here c is a constant. Does anybody know what sort of restrictions are on our choosing the constant? What happens if I chose c equals -1? No, it won't work, right? So whenever you're choosing these constants, you've still got to have some common sense. I can only choose different values of c for c non-negative, right? So let's start off with something real simple. So if c equals 0, then what are we going to get? Well, just replace c with 0, and you're going to get some sort of equation like this. So what's the solution to that bottom equation? What x and y satisfy that? Right, x equals 0, y equals 0. That's the only explanation. So our curve of intersection isn't really a curve at all, it's just a point. All right? Well, let's put in, say, c equals 1. So we go up here, put in c equals 1. What's this curve? An ellipse, right? Okay, now I haven't drawn anything yet. I'll draw something in a minute. And I'm going to choose another one, c equals 4. Now I could choose c equals 2 or c equals 3, but it's not going to give me the nice numbers that I really want. Okay? Okay, so over here I'm going to get 4 equals x squared plus y squared on 9, which is another ellipse. Okay, I can just bring the 4 down, I'll get 36 down here and 4 down here. So let's actually draw in some of these curves and see what's happening. All right, so when c equals 0, I'm in the xy plane and I get the point 0, 0. So that's not very exciting. If I'm, I guess, in the plane c equals 1, which is, remember, the plane parallel to the xy plane, 1 unit up, I get an ellipse. So I'll get something like this. That's the contour curve. I've just drawn the ellipse in the plane z equals 1. If I go up to, say, 4, I want to draw this ellipse here, which again is just a slightly bigger ellipse. Now, so these are the contour curves. Let's draw the level curves. So all we do is we smush these things down, and so we're going to get these sort of curves. Okay, so how do we put it all together? Well, there's one more thing that we'd like to do. Can anyone remember what's left to do? Yes. Let's do some intersections with, instead of horizontal planes, with vertical planes. So this is the second and last thing. You don't have to do this every time, but it's a good idea. So intersect surface with vertical plane. Now I'm just going to choose something like x equals 0. because again, it's quite simple. So what I do is I go up here and I let x equal 0. So I'm going to get z equal y squared on 9. So what kind of curve is that? Z equals y squared on 9. It's a parabola, right? So, if I'm staring down the barrel of the x-axis, so the x-axis is coming out like that, this is the parabola. Okay, badly drawn, but you get it. So, how do we put those two things together? Well, look at all the curves. Essentially, you take this curve and put it up here, and you just connect the lines. Oh, it's ruined it. Okay, it's smooth there. Okay, that's our surface, even though I've ruined it a little bit. Sorry, YouTube. Give me the thumbs up. Now, who's pretty comfortable with that? Who remembers that from last year? Okay, good. You should. Okay, so you've got the y-axis hanging out over here. Now, contour curves. One of the ideas that you may have seen with contour curves and level curves is in maps. With maps, you've got to sort of give you only got 2 dimensions to work with, right? But you want to give a 3-dimensional understanding. Let me give you an example of how you can use these things in daily life, I guess. This is a picture of my parents' block in Brisbane. Don't worry, they didn't get flooded. You might be able to see the outline of the house. So you're looking down from space. You've got the outline of the property here. Okay, with some stairs and stuff. Here's the rear of the property. Here's the front, the street at the front. Now the lines on the site map are just level curves. Okay? And walking along one of these lines would mean that you're walking along a level, like you're not going up and down, you're just walking along a level path. Okay? So that's one of the nice applications of level curves. Now you may think, what's this AHD up here? 25.216 metres AHD. Anybody know? Oh, who said that? Can you say it a bit louder? Yeah, can you say it a bit like, what is it? Do you know? Right. So with old surveying, I think they used to use sea level. But the problem is sea level rises and falls. Okay? So they thought, oh, let's have a basis measurement that's uniform and doesn't change. And so relative to that, this is like 25 metres above that or something like this. Am I right? I'm not a surveyor. Yeah. So, okay, good. Yeah, so this is important, right? And of course, again, if the curves were close together, you'd see, a big slope or a big hill associated with that. So let's have a look at some. Actually, before we get to that, we can step it up. This is something you haven't seen in first year. We can step it up to form level surfaces. So functions of 3 variables. You just follow the same kind of method, set the function to a constant and then vary that constant. So for example, let's say I had the function, this. Does anybody know what the level surfaces of that function would be, geometrically speaking? I'll tell you what, I'll leave you to think about that. Let's look at some common surfaces and their properties. Now, again, this hasn't been talked much about in first year, but what these pictures, I hope, do for you is give you some real insight into how the surfaces can be formed from just intersecting the surface with various planes. So you can see here, this ellipsoid has intersections of ellipses. Okay, if you cut it with some plane parallel to the xy plane, you'll get ellipses, or circles maybe if A and B are equal. And if you do vertical cuts, you're still going to get ellipses. So you can hopefully see how it all comes together. It's also very important to remember the equations associated with these because, like I said, in second semester, in the second half of this course, you're going to have to integrate over surfaces like these. So you need to know the surfaces really down to the ground, or the equations for them at least. Here's a paraboloid. So you can see the horizontal cuts are going to be ellipses, just like the one that we did. And the vertical cuts are going to be parabolas. Put them together, you get what's called a paraboloid. And here's the equation. Here, A, B, and C are just constants. Hyperboloid. So this time the vertical slices are going to give you hyperbolas, and the horizontal slices are going to give you ellipses. So here's a two-sheet hyperboloid. Again, the horizontal slices are going to give you these green ellipses, and the vertical slices are going to give you these hyperbolae. Cones. Cones are really important in this course. The vertical lines are going to be, the vertical intersections are going to be lines. The horizontal intersections are going to be ellipses. Now with this one, this is the one we looked at before, the horizontal slices are going to be hyperbolae, and the vertical slices are going to be parabolas. It's really good if you can, there's a lot of information to take in on these sort of half dozen graphs or something, but try to learn them, get to know them. Okay, you'll find this course really much more manageable if you can just go, oh yeah, that's a paraboloid, or that's an ellipsoid or something, just by looking at it.